Hey guys. All right. So today what we're going to do is we're going to look at implicit differentiation. The key here is that it's algebra. There's going to be a lot of algebra in order to figure out how to take the derivative of things when we have more than one variable. And then algebraically being able to solve for that. So if we look at this, the bell work here is basically just for you guys to look up some things and kind of understand what does implicit mean. Okay, so go ahead, go through that on your own. Pause the video, look it up, use these definitions, etc. Right? But essentially it's like, well, what it says here is like it's suggesting it's not directly expressed, and that's exactly what's going to happen here. Our derivatives are not going to be directly expressed, but we're going to find them. All right, and then normally what I would do is get you guys to write down a bunch of stuff or discuss it at your table. But since this is a video, that's not going to happen. So far, most of what we've done has honestly been a lot of algebra, right? And what we've done is we've usually looked at it very explicitly, right? When x and y, and we can isolate y, then we can explicitly tell us whether or not something is a function or not because of the vertical line test, which is something you've done before. And then we break it up when we have things that are not functions. Like this example here, we break them up by doing two separate functions, the positive and negative version, which would give us the two things that together are not a function, but individually they are by limiting our range or our domain, depending. Just the range. Okay, so when we look at this, let's jump down a little bit further. Okay, so alternative notation, you've seen me use it. We have f prime of x, but I've also used a couple times like dy dx or d dx, okay? All this means here, that's a little bit I guess specifically different than saying f prime of something, is that this here is going to be referring to the derivative with respect to x. So whatever the one on the bottom. So if it was like dx dy, we'd be taking the derivative with respect to y. Okay, so what we're going to do is be able to develop that so that then we can differentiate things like this original equation before it's been implicitly solved for y. So the x squared plus y squared equals 25. So when we explicitly do that, right, we end up with this equation. This is the explicit. And to take the derivative of this is something that we know how to do. It's a little bit tricky or annoying, but we already know how to do it, because what we're doing is when we're taking dy dx, so the derivative with respect to x, we know that this is the same as being to the power of 1/2. And at this point, you guys are great to know that the derivative inside goes on top, and then we end up with the 1/2 portion, and then we literally write the exact same root that was there on top, because now it's on bottom, because 1/2 minus 1 gives us negative 1/2, which means we can put on the bottom, and that allows us to solve or simplify by crossing out those 2's, and so we get that dy dx is simply going to be negative x over the square root of 25 minus x squared. Okay, now if we look at the explicit version implicit, my bad, then what we're going to do is we're still going to take the derivative. So if I take the derivative of this, let's start with the original equation. Okay, well, you know how to do 2x. That's easy. It's just 2x. And because we're taking the derivative with respect to x, that's all we got to do. Now, for this one, it's a little bit different. We're going to go 2y, which would be how you might expect it to be. But because we're differentiating with respect to x and not y, we need to actually say, hey, we took dy dx. We took the derivative of y. Okay, and we did it with respect to x. And then, of course, this is going to be equal to 0 because it's just a number. Okay. Now, from there, what we do is we're going to have to start solving for this dy dx. So what I'm going to do is I'm going to move over the 2x so that I get 2y dy dx. And if you prefer, because honestly writing dy dx is annoying, you can write y prime. That's fine. And I will do that in later examples. So this equals negative 2x. Then we're going to divide this by 2y. And that, of course, cancels here. The 2's are going to cancel here. And so we get that dy dx is equal to negative x over y. Now, you'll remember that at the beginning of our equation, y could be solved as the square root of 25 minus x squared. And so if I make that substitution, because of course it's hard to do if I've got two variables still. So if I put that substitution in and say, well, this is the same as 25 minus x squared, you'll notice now that these are exactly the same. So it didn't matter which way we did it. And so we can often choose the way that is easier, or sometimes we have to do it implicitly because we don't have a way to easily separate them. Okay. So basically what this means is that this is the same derivative in different forms. And I say different forms, of course, only if we haven't done that substitution yet. So it would be this version. As soon as you make that substitution, it's no longer different forms. It's the exact same form, right? But that's just so you can see how they're the same. All right. So where is this going to be useful? It's things like this, right? When we've got circles, because we already know that I can't take a circle and I can't make it as a function. So I'm going to have to like write it and then implicitly differentiate. So consider the graph of the circle here, find the equation of the circle in implicit form below. So hopefully you remember that to find the center of a circle, right, we can then write it as x minus the x coordinate squared plus y minus the y coordinate, which is minus -2, so plus 2 squared, and it's equal to the radius squared. So my radius here is 1, 2, 3, 4, 5, so 25, or 5 squared if you prefer. Okay. Now let's implicitly differentiate the equation of that circle. So these here, you can probably guess, these are going to be some chain rules. So we're going to get 2 times the original thing. Then we have to multiply it by the derivative of the inside, which in this case is easy. It's just 1. Okay. Now this one is the one that's a little bit trickier because it is still going to be 2 and then the thing that's inside times the derivative of the inside, which is 1. But remember, if we're differentiating y, then we're also going to have to write dy dx. And of course, if we differentiate a number, it becomes 0. So now from here, we're going to need to start solving things so we can get this dy dx by itself. So probably what's easiest here is to divide everything by 2. Because if I divide everything by 2 here, 0 divided by 2 won't matter, and this will get rid of all these 2's for me. Okay. Now, that only really helps because it's in every term. If it wasn't, it wouldn't be helpful. All right, so now I've got x minus 3 plus y plus 2. I'm going to put this one in brackets because, of course, it's important to remember that the dy dx is multiplied by all of that. Then I can move these 2 over. So minus x plus 3, minus x plus 3. Those, of course, cancel. Now I'm going to get y plus 2 dy dx is equal to negative x plus 3. And hopefully you can figure out that last step now. I just need to divide by this y plus 2. And I'm running out of a little bit of room, so I'm going to write it over here. So my dy dx is going to be equal to negative x plus 3 over y plus 2. And that would be my derivative. Okay. Now, obviously, you can also sub back to get rid of like the y if you need to, but in this case, we can leave it this way, okay? Because sometimes we can actually use it by just having the x and y point. Okay, so complete the table below, finding the value of dy dx at each of the indicated points. Then draw the graphical representation. So this is how you can see. If I have the entire point here, then what I can do is I can take my dy dx and I can plug it in. So instead of being x, it's going to be 0 plus 3 over, instead of y, it's 2 plus 2, which means I'm going to get 3 over 4. Okay. And we're supposed to draw in that tangent line. So this is at the point 0 and 2, so right here. And I'm supposed to get one that has a slope of 3 over 4. So that's a rise over run. So we need to go like 1, 2, 3, 4, 1, 2, 3. So up here. And that should be our tangent line. Let's try and use some colors to make this easier on you. So now if I'm doing this one, right, and I'm going to switch it to y prime, because again, they mean the same thing. So it's good for us to get used to doing both here. And so this time my x is negative 3 plus 3 over 3 plus 2. Well, which is 0 over 5. So we go up to my point 3, 3. Right here, you can see that that's clearly a maximum, and so it makes sense then that my tangent is going to be horizontal like that. All right, let's keep rotating colors to help make this easy. So dy dx, just to keep switching it up for us, is going to be negative 8 plus 3 over negative 2 plus 2. Now, the problem here, of course, is that I'm going to get negative 5 over 0, which means that it's undefined, which we also know, forgot my E, there we go. Undefined also means it has a vertical tangent, right? Because the run is 0. So this was over at my point 8, negative 2, so right here. And I'm going to get something that's straight vertical like that. Let's continue our color wheel. We go light blue. So dy dx is going to be equal to negative 3 plus 3 over negative 7 plus 2. And again, I'm just plugging in my x and y coordinates here, right? And so that gives me 0 over negative 5, which again is going to be that horizontal one. So we can go up here to 3, negative 7, which is right there. And sure enough, you can pretty easily see that it is definitely a horizontal tangent because it's a minimum. Keep it up. Let's go to our purple. Why not? dy dx. We plug it in. So negative x plus 3 over y plus 2. This gives us negative 3/4 this time. So now at 6, 2, we're up here. We want the same line as that blue one, but this time it's going to be negative. So 1, 2, 3, 1, 2, 3, 4. And so this time it'll look like that. We're running out of colors. Let's see. Let's go yellow. So dy dx. This one's going to be negative, negative 2. So 2 plus 3 over negative 2 plus 2. And you can probably already see here again, that's going to be the other vertical one. It's the other side. So that's over here. And we got one more. We'll use red. So dy dx here is going to be negative x plus 3 over y plus 2. And so this is negative 3 over negative 4, which is 3/4. And so at 6, 6, or 6, negative 6, sorry, right here, we're going to get that same one that we had before, the 3/4 one. So 1, 2, 3, 4, 1, 2, 3. And so we get that one. So there's all of our different tangent lines. And so you can see here, as I was kind of saying, like, it doesn't matter that we have an x and y in our derivative as long as we have the coordinates of the point. So because I have the coordinates of that point, I can just plug in my x and my y and still get my derivative, just like we did before when we only had x. So it's not really that big a deal. And if we really want to, then like we did in the previous example here, we can always like sub back in what y is. But you really don't need to as long as you've got the x and y coordinate for your points of tangency. Okay, let's keep it going. Let's apply this to a few other things. And so for this one, all we're going to do here is find our derivative. That is the only thing that we're going to do. So we have to remember that if we're taking dy dx, right, that means if it's not x, we have to write the derivative. So this one here is going to be 2y, and I'm going to switch to y prime, okay, just because it's easier for us to write and kind of see. They both mean the same thing again. This one would be just 2, and because it's x, I don't need to write anything. And this one here would be 3, but I need to write that y prime. Okay? So then from here, you can see like my issue is I've got 2 y primes, which we haven't had to deal with before. So I need to put them together, right? So what I'm going to do is I'm going to move this one over. Because now I can get 2y prime minus 3y prime equals 2. And you can probably guess now I'm going to pull out that common factor of y prime. And now that allows me to divide and get that y prime entirely by itself. And so y prime is going to be equal to 2 over 2y minus 3. Okay? So, and again, this is also like dy dx. Let's write that in just to help us remember that these things are equal. Good? Now, if you want to immediately, when you put them on the same side, pull out that common factor of the y prime because you know that's what you're trying to do, that's fine. You can do that. So let's maybe try that on this next one. So implicitly, I'm going to just take the derivative. So it's 2. X is already the one we're doing. This one here, the derivative of y is 1, but remember, that means I need to write y prime. E to the y equals 2x, no need x prime because it's already with respect to x, and then minus 2y, it's an ugly y, still ugly, but whatever, y prime. Now again, we need to put those two on the same side and put everything else on the other, so let's move the negative 2 over, And let's move the 2y prime over. Okay, so now at this point, these cancel, and I've got my y prime. So I know that the whole point is to pull it out. So I'm going to pull it out right away. Okay, and now I've got just e to the y plus 2y, because that y prime I pulled out as that common factor. That's the whole reason we did this. And then 2x minus 2. And I'm sure you can see where this is going now. What I need to do is divide both sides by whatever is multiplying the y prime. And so we can see that y prime is going to be 2x minus 2 over e to the y plus 2y. Awesome. Not too bad. All right, so if we look at this one looks a little bit trickier, and it's this part right here, because that, of course, is going to be a product rule, right? So I need to worry about the fact that I've got to take a product rule, and I got to do it implicitly. So that means I'm going to take the derivative of the first, which is 1, because the derivative of x is just 1. So it's going to be 2y. Then I need to add to that 2x times the derivative of the y, which is y prime, because it became 1, but it's y. So I need to show that I took the derivative of it. This is going to be 6y prime, because again, I'm taking the derivative of y, not x. And then this is just 2, because I don't need to show that I'm taking the derivative of x, because that's what we're solving for, is dy dx. And again, that's just because in this case, we're saying that y prime is equal to dy dx, okay? I just don't like writing dy dx everywhere because, of course, that's a lot more work. And it doesn't matter which side we move these on, but we do need those two y primes on the same side, and we need everything else on the other side. And since you're awesome at algebra, we're going to do it all at once to save time. Then I'm going to pull out that common factor that I forced to happen, which is that y prime. I'm going to get 2x minus 6y. And that's going to be equal to 2 minus 2y. And then sure enough, you can see we just divide again. Because the whole goal here is to get the y prime by itself. So 2 minus 2y over 2x minus 6y. But I would not stop there, because in this case, we can see that there's a very easy common factor here. Everything is divisible by 2, technically because we're writing it like this, which you should not need to do this. But if you're having trouble with the algebra, that's what you should do to kind of prove, because some of you still try to cancel things out that you can't cancel. Okay, so it should look like this. And so then I've got y prime is equal to 1 minus y over x minus 3y. Awesome. Like I said, if you're having trouble with this, do this, please, because a lot of you are still trying to cancel things out that you can't because they're not common factors everywhere. It has to be everywhere in the numerator and everywhere in the denominator, or you cannot do it. All right, let's take a look at this one up here. We're just going to keep going through the same motions, right? So this one's going to be 15x squared plus 0, because that goes away. So that equals 2y prime, because the y went away. And then we got another product rule here. So minus, let's maybe do it this way, and show that it's 6xy plus 3x squared y prime, because I'm taking the derivative of x here and then derivative of y there. All right, so now I'm going to need to distribute that negative in. Honestly, do that like while you're doing this usually, but I know that some of you guys have had some trouble with algebra, so that's why I'm separating it into a separate step there. So minus 6xy minus 3x squared y prime, and you can see that the y primes are already together, so all I need to do is get rid of the thing that are not y primes. So then I've got 15x squared plus 6xy equals, I'm going to automatically pull out that prime, and I'm left with 2 minus 3, hitting myself, my picture, 3x squared. And so then, of course, 1 second, guys. All right, so then we're going to divide by everything that's next to that y prime. And so I've got kind of an ugly looking equation there. And unfortunately, nothing actually simplifies if we look at it. Because I don't have any common factor. Almost have an x, almost have a 3, but I don't quite have it everywhere, so it won't work. So that's going to be our final answer. And let's not cross out the answer. There we go. All right, let's keep going. Let's do a couple more examples of this and apply them a little bit more. So normally if we were doing this in class, you can see I had to throw a break in there. But since it's a video, you can just pause it whenever you want. All right, for what values of x will this curve have a horizontal tangent? Okay, so we need to figure out what is the derivative of this. We need to make it equal to 0 because that would be our horizontal tangents. Okay, so first we just take our derivative implicitly, 3x squared plus 3y squared, but this is y, so y prime, equals, here's our product rule, so 4y plus 4x y prime. And the 1 goes away entirely. Now I need to put my y primes together. And I need to move over everything that doesn't have the prime. So I've got 3x squared minus 4y equals, let's pull out that y prime first, like we did before. 4x minus 3y squared. And of course, our last step is to divide so that we've got it by itself. Oops. Like so. And so I've got 3x squared minus 4y over 4x minus 3y squared, and that's going to be equal to my y prime. But now what I need to do is I need to make that thing equal to 0. So instead of making it equal to y prime, let's make it equal to 0. Over 4x minus 3y squared. And if we look at this, we know like the bottom being 0 is not what's going to make this 0. It's going to be the numerator. So I'm really just going to focus on the top here. And so I've got that like 0 is going to be equal to 3x squared minus 4y. And then what I can do is I can solve for y in this case. So y is going to be equal to 3x squared over 4, because I can move the 4y over and divide by 4. So then I've got whatever my y is equal to. Why is that helpful? Well, because now I can go and take that and plug it into my original equation in order to try and figure out where this thing will be 0. So I'm going to get x cubed plus 3x squared over 4, all cubed, plus 4x times 3x squared over 4 plus 1. And so now I can take this and I'm going to need to simplify that exponent. So x cubed plus 3 cubes, 27, x to the 6th over 4 cubed is 64, plus, actually I'm not going to multiply those because the 4 can cancel with the other 4. So I'll get 3x cubed plus 1. Okay, now at that point, I'm going to solve that graphically because that's pretty messy. And so if we give you a question like this, we're definitely going to let you solve it graphically. So I'll let you plug that in. Sorry, I missed the equal sign, didn't I? Should be an equal sign here between these two, which makes it a whole lot easier to graph. And so then we can graph this on the left side, this on the right side. And when I do that, I'm going to get negative 0.77 and no, not 1.732. So if we do that, we get our two different solutions for it. All right, so then what we want to do is we want to take this next one here, and in terms of y, describe the values of x for which the curve here will have a vertical tangent. So if it's got a vertical tangent, this means the opposite of what we did before. We want it to be undefined, right? So this is going to be when dy dx is undefined. Those are the points that we're looking for. Therefore, this is going to be when, and so I need to, this is the exact same equation. So I want to look at this one up here, right? But I'm going to look at the bottom. I'm going to look at the denominator. So that denominator was 4x minus 3y squared. And I want that to be equal to 0 this time. Okay, so once again, when I do that, I'm going to have to go ahead and solve for one of them. This time it's easier to solve for x for sure. And so x would be equal to 3y squared over 4. And then same as we did before, we're going to plug this in, plug into the original, and solve for x. Now, we don't actually have to do that because in this case, it says describe them in terms of x, which we've done. But if we wanted to go further, that is what we would do. All right, so the only difference here is that you'll notice here we've got that other notation we've used before, which is d squared y over dx squared. And so that just means we're taking the second derivative. So we're going to start by finding the first derivative. So 2y y prime plus 2y prime equals 2. Okay, still got to do the same thing. I'm going to have to solve for y prime. 2y plus 2. Then we're going to divide both sides.
I think they're coming.
Yeah. And if you can see here, you can see that there's that common factor again as well. So we'll write it this way. And then we keep going. So now I need to take the derivative of this, which I'm going to have to pause, and I will do it later. All right, sorry guys, I just had to switch rooms there. My room was being used, but we can continue here. So now when I'm taking the derivative of this, first of all, it's probably easier for us to write this thing here as y plus 1 to the negative 1. Okay, and now what we're going to do is we're going to take the second derivative. So when I'm taking the second derivative of this is where I'm going to get my y double prime, or d squared y over dx squared. And over here, I've got to do a chain rule. So I'm going to put negative in front, exactly what was there before, to the negative 2, multiplied by the derivative of what's inside, which of course is 1 times y prime. Now this is where things get a little bit interesting, because what we need to realize here is that this y prime, we've already figured out what it is, and so we're going to substitute in this value up here, right? Because we know that that's what y prime equals. So our y double prime is actually going to be equal to negative 1 over, and if I've got y plus 1 squared times y plus 1, we'll write it out the long way first here, but some of you have probably already seen it. Really, all I need to do is take that and put those all together. So my y double prime is actually going to be negative 1 over y plus 1 cubed in this case. So it works out nice and easily, and that would be our second derivative. So let's try it again here. We got one more example to practice this. We're just going to do a basic circle here around the origin with radius 1. So in other words, your unit circle that you all love so much. So if we take the derivative of this is going to be 2x plus 2y y prime, and it equals 0. Now, of course, I can solve for that y prime, and so I'm going to get 2y y prime equals negative 2x. I'm going to divide both sides by 2y, and we'll get that y prime is equal to negative x over y, which we did earlier in the lesson. Now I need to go ahead and take the derivative of this again, so that'll be y double prime is equal to, and now I got to use quotient rule. So low d high, which is going to be just negative 1, minus high d low, which is 1, but y prime, over y squared. Now, that is really awkward, and you should definitely simplify all those negatives, because I can almost guarantee you that you're going to make a mistake otherwise. So this is negative y plus xy prime over y squared. And then, of course, we know that's a really bad looking y prime, ain't it? And this y prime here, of course, is this. So that's going to come down and become my y prime. So I get negative y plus x times negative x over y squared. Now here what I need to do is simplify these things a little bit. So if I've got fractions of fractions, I'm going to need a common denominator. So this one's going to really become y squared over y, because I'm multiplying by 1, because now I've got that common denominator, right? So I can put them together. So now my second derivative is going to be negative y squared minus x squared over y, and then over y squared. But really, if we're a fraction of a fraction, we know that instead of doing that, we multiply by the reciprocal, keep, change, flip. And so actually, we just get negative y squared minus x squared over y cubed. And that would be our final answer there. Hopefully that makes sense. If you need to, go back and watch that one again, because it is a little bit tricky there with some of the algebra. I don't think the calculus is hard, but that simplification, I know some of you struggle with fractions. So take a look at that. And we're just finding a common denominator, then dealing with the fractions over fractions to get it into a single fraction, right? We're never going to write things as fractions of fractions. We will always simplify them. I shouldn't say always. We will almost always simplify them into being that single fraction. All right, guys, that's going to be it. And I will see you next time.